plus our remainder over our divisor. Just like with the 15 and the 4, right? We had, what was our remainder? We had a 3, didn't we? So we put 3 over 4. Yeah. Now what? Yeah, now, I mean, that's an integral we can do. We don't need any more work. So this section is called partial fraction decomposition. We did not need partial fraction decomposition for this problem. We needed long division, and now we're done. The next problem we'll need to do more.
How did we get the x squared from in the first place?
Hold on.
You said we're done.
We're done as far as we don't need to do partial fractions.
Okay. Yeah,
We can just do the antiderivative each one. Okay, what now?
How did we get the x squared from in the first place? The x squared on top, you know.
I said, what do I multiply x by to get x cubed?
Right.
X squared.
Yeah.
Mm-hmm.
And technically that what's being long divided is like x cubed plus 0 plus x.
Yes.
Right.
That was to keep a column for my x squareds. That's why I put that in here.
It's important to separate them into columns just to kind of like make the math a little easier to digest.
It's what I just said. It's to keep a position for x squared. Right? If that wasn't there, then where do I put the x squared? Right? I need a position for it. So that's the standard technique. Anywhere you're missing a variable, you place a 0. All right, so antiderivative of these, I just do one by one, right? Okay, the first 3 should be trivial, right? Just power rules on those. And then the last one is a constant over linear, and that we did last class. This is a natural log. Do we have to scale? Other than the 2, do we have to scale at all? No, because the denominator is linear and has a 1 here, right? So there's no scaling involved. So it's just going to be the 2. I'm going to put the 2 out front. Natural log of x minus 1 plus c.
This was like the rules like 17 or something like that.
Not rule 1718. It's after we looked at that last class, right? It's all these things we did, right? I spent all class last time going through these things saying, hey, if we ever see constant over linear, we can handle it, right? This, constant over linear, constant over repeated linear. That was all last class, right? And now we need it. Now we need that, right? All right, we're done with that problem. Let's move on to the next one. Try and find the antiderivative of that. So when I look at this, I'll just tell you what I think. First time I look at this, I say, okay, rational function, polynomial over polynomial. But I notice right now that the degree of the bottom is 3 and the degree of the top is 2, right? Maybe a u substitution would work. Because if you have a 3rd degree polynomial, if you called that u, the derivative would be what degree? Second degree, right? Maybe the top is actually the derivative of the bottom and I get lucky here.
But you wouldn't be able to, there's nothing you could multiply by to make the exponents match though, right? Or the coefficients. So, I mean, you could do it, but you'd have to multiply by 3 different numbers on top to get the right coefficients.
Yeah, you would have to get everything right, right? So, but what I'm saying to you is that I'm not diving completely into partial fraction decomposition yet. I'm not. I'm actually going to check this real quick just to make sure. If I take derivative of this, I get 6x squared plus 6x minus 2, right? That's what I get? And then I just check real quick, all right? Just check real quick. Is the numerator, am I off by a constant or is it more than a constant I'm off by? I'm off by more than a constant, okay? So I just wanted to check that because Again, what if it was this? What if it was just off by a constant? Then I would just use basic U sub, right? You follow me? Okay. I've given a problem like that on a test before, where it was just basic U sub, and students took like 30 minutes to do the problem because they didn't do that first. So, but it's the more important part of this is the thinking about third degree. Okay, if that's U, the derivative is going to be quadratic, and I have a quadratic. Maybe a basic U sub would work. Maybe.
So it's always,
It doesn't though, right?
Is it always good to try to do U sub first?
If something is leading you that way, what's leading me that way is I've got third degree in the bottom, second degree in the top. If I had fourth degree in the bottom and third in the top, I might look at that as well.
You got to develop the instinct for it.
A little bit of instinct, exactly. So that's not working though.
When it comes to like our final or third test, whatever, are we gonna have a column, like this, whatever, we're gonna have like, oh, we choose, trig sub, U sub, partial fractions, like.
Wait, are you what?
Is it
On your
like,
next test.
We have these like, or not next test, like the test later on towards the end of the semester.
Uh-huh.
We're gonna have, where we can choose any 5 of those, integration techniques. And we're just gonna be like, oh shit, which one do I choose?
That's your next test. Yeah. Yeah, your next test, one of the challenges of that test is you knowing what technique to use. Like you're not going to be prompted, hey, this is a trig sub problem, right? But there are things that tip you off. I mean, there are things that you look at them and you're like, okay, I've seen this. I've been through this before with my homework. I know what I'm dealing with here, But yeah, that's the nature of the beast. Because in the real world, you get an integral, like, no one's going to be like, hey, and by the way, that's trig sub. But you're going to use a computer anyway, right? So, all right, let's just keep going. So I look at this and I go, crap, there's nothing I can do. So what I'm going to start with here is looking at the numerator and denominator. Do I need long division? Why not? The power on the bottom is bigger than the top, right? So no long division is necessary. What if these were the same powers? Do you do long division if they're the same?
Maybe.
Yes, you do. Okay? Yes. The only time you do not do long division is when this is bigger than that. If these are equal or the top's bigger than the bottom, then you do long division. All right, so no long division. So the next thing I need to do is see if I can somehow rip this apart using partial fractions. But to do that, I actually need to see what my denominator is made up of. So I'm going to start trying to factor my denominator. Pull out an x first. So if I pull an x out of the bottom, I'm left with 2x squared plus 3x minus 2. Okay, this is just factoring, right? That's a GCF. And what's left here, this is a trinomial, right? Hopefully it factors. And we're all calculus students, right? We somehow got through Cal 1, somehow got through college algebra and pre-cal, which means that we should be able to factor a trinomial given enough time and effort, right? That's the factorization of that quadratic. Do you all agree with me on that?
Is there a shorthand?
No,
Okay.
you need to, yeah, you just got to be able to do this.
gotta do it.
Yeah, this I'm using like guess and check. I'm just doing like kind of playing with the numbers. So I'm gonna double check it though. 2x squared plus 4x minus x, that's 3x minus 2.
Because if you're pulling out trinomials, they generally have to be like 1 or 2, right? They have to be a factor of the numbers that are already there. So
Yeah,
like 2.
exactly. All right, so my integral, I don't care about the numerator. What is my denominator made up of? This is a linear factor. This is a linear factor. This is a linear factor. They're all different, right? They're all different from one another. So what that means is I should be able to take this somehow and break this down into a number over this, a number over this, and a number over this. So I'm going to go do that now. So this is separate. I'm going to come back to this problem. I'm going to come over here, and now comes the partial fraction decomposition. I start by writing what I'm trying to decompose. This is what I'm going to try and decompose. And like I just said, for each linear factor, I have to put some constant that I don't know. And my task now is to figure out what's A, what's B, what's C. If I can figure out what A, B, and C are, do you all agree that this integral, if I integrate this, it would be much easier to integrate this, right? Because this, and this are all constants over linears, and those are going to be logs, natural logs, when I integrate them. So I really want to make it look like this, right? When I teach this in pre-cal, I tell my students, I understand this sucks, but this actually makes life easier in Cal 2 because we get to a point where we have a problem we cannot do, but if we can decompose it, then it becomes an easier problem, much easier problem. All right, here we go. So what's the technique? This is the first time we've actually done the technique of partial fraction decomposition.
You're going to multiply a by 2x minus 1 and x plus 2.
Okay.
Or you're technically multiplying it by everything, but the x cancels out.
Okay.
Multiplying by the greatest common denominator. Whatever, I just said wrong. And then it didn't come out right. But
You're, no, I know what you're saying. What you are thinking is correct. It's not coming out exactly right, but I'll clean it up for you.
all right.
So we are going to multiply both sides of this equation by the least common denominator, or by this, by that. Just multiply both sides of the equation by that. That's your first step. So if you multiply here, x, 2x minus 1, and x plus 2, right? If you multiply on the left side, everything just goes away, doesn't it? Well, not everything. The top's still there. I still have what? X squared plus 2x minus 1. That's what would happen on the left-hand side. But you have to also multiply the right-hand side by that same thing. This will always be your first step. You're essentially clearing fractions is what you're about to do. Clear the fractions. So I multiply the left side by this. All that's left is the numerator. And then when I do the right side by this, because this is 3 terms, this must distribute through to each of these. Okay, so when I do a over x times this, what happens? What happens? I'm going to write this one on the side here. If I do a over x and I multiply times x times 2x minus 1 times x plus 2.
You get 2ax minus a, the entirety multiplied by ax plus 2a.
But the x's go away.
Yeah.
Yeah, that's what I want. I mean, we need to see that's what happens on the first multiplication. The x on the bottom and the x in here cancels out. So all you're left with is the a, the 2x minus 1, and then the x plus 2. That's your first distribution through. Now, on your second distribution from here to here, the b stays, and what cancels this time? This 2x minus 1 kills off one of these, and you still have what? X and x plus 2. And then your final distribution here to here, your c's still there, and this time the x plus 2 cancels with this x plus 2, so you have x and then 2x minus 1. It's just algebra, right? That's all this is. I know it's been a while maybe, but it's just algebra, right?
Even the tutors and the tutoring lab that can only do algebra could infinitely help you better than yourself.
Agree. All right, now what? Right? What do we do at this point? That's, you know, there's a lot of different kind of approaches here. What are we trying to do? Find A, B, and C, right? That's what we're trying to do. Figure out what A is, figure out what B is, figure out what C is, and then we're done. So what I'm going to do is show y'all 2 different ways of doing it. There's kind of like a shorter way and a longer way, like an easier and a harder. The shorter way doesn't always work though. So the long way is longer, but it will always work. I'm going to show you the short first, right? So the short method, you always want to try this first if you can. We're trying to solve for A, B, and C, right? So I want you to look at this expression. And I want you to see if you can pick a value of x that will kill this off and kill this off simultaneously. Is there a value of x that you could plug in that would eliminate that term and not eliminate this term?
Is it a factor of both terms?
It would have to be a factor of both terms.
X equals 0?
X is 0. Look at that, everyone. If x is 0, do you all agree this all becomes 0? If x is 0 here, do you agree it becomes 0?
Yeah.
If x is 0 here, these don't become zeros, right? So I'm going to be clever right now, and I'm going to let, it's one of the few times in math that you have control, I'm going to let x be 0. I'm going to make that choice. If I let x be 0, I'm now going to rewrite this entire equation, replacing all x's with zeros. And let's see what we get. 0, 0. Left side is now what? -1 equals, okay, be careful here. A, parenthesis, what happens here? 2 times 0, take away 1, -1. 0 plus 2, 2. And then plus, what do we know about these? They're gone. 0 plus 0, right? Those are gone. By design, right? By design, by our clever choice of A. All right, that's just the equation. That's just -1 equals -2a, right? That's all that is. -1 equals, these two multiply is -2 times a. And just solve for a. A is what? A half. Positive a half. Boom. Okay, 1 down, 2 to go. So now I'm going to go find b. Can you think? So all of this right here was us trying to find a, right? Now let's try and find b. So I'm going to let x be something. A half? Why?
Because 2 times 1 half is 1 minus 1 makes 1 plus 0.
So you're seeing that the difference between this one and these two is that these two have the 2x minus 1 factor in them, right? This one doesn't have that 2x minus 1 factor. So if there's a way that I could turn these two into zeros, then it would kill those two off and it would maintain this one, right? Yeah? So how do you make this 0? Well, set it equal to 0. You set that equal to 0, what do you get? A half. Or you can just visually inspect it. 2 times a half is 1, 1 minus 1 is 0. So do y'all see what I'm saying? I'm trying to figure out what b is. So I look at what two factors are in these that are not in here. And that's the 2x minus 1. I set that equal to 0. I get x is a half. And that's what I'm going to let x be. So x is a half. And now I play the game again. I plug in a half in this. That's going to kind of suck. A half here is what? 1/4. Okay, plus what's 2 times a half? 1. Take away 1, right? Equals. Okay, what's going to happen when I plug a half into this? 0, right? That goes away right here. And then plus, now this doesn't go away. B times a half. And then this is a half plus 2, right? A half plus 2? 3 over 2, or 5 over 2. 5 over 2. I'm going to use 5 over 2. Again, I don't want to use mixed numbers. So a half plus 2, you have to get a common denominator. That's 5 halves. Okay, and then plus, what does this become? 0, right? Because that zeroes out. Let's see. This is b times, let's see, if we put these two together, we get 5/4, don't we? Just multiply. So I'm going to put that 5/4 in front of the b. And now I have to solve for b. So however you want to do that. 1/5? Yep. Just multiply both sides by 4 over 5, the reciprocal. So b is a fifth. One more to go. So all of this was to try and figure out what b was. Now let's go get c. And again, I look at c, and then I look at these, and I say, what factors do these have that this doesn't? And that's the x plus 2. So what do you have to plug in to make that 0? -2. So I plug -2 into all the x's, and I do it again. Let x be -2. Plug in. Negative 2 there is positive 4. Negative 2 there is minus 4. Minus 1 equals, okay, that's going to go to 0. That's going to go to 0. And then I just need negative 2 into that last one. C times negative 2. And then 2 times, what, 2 times negative 2 is negative 4. Take away 1, minus 5. The left side of this is going to be just negative 1, and then this is going to become 10 times C. Negative 2 times negative 5. So C is negative 1/10. Bam. This is the short method. This is the short method.
This is shorter.
This is the short method.
Like 30 minutes.
Okay, we're ready to set up the integral, right? So look, we said that original expression right there. We said we're going to go handle that, but let's go break it down first. We did the partial fractions, and we said it's going to turn into something like this. We need to figure out what A, B, and C are, and we just figured out what A, B, and C are. So now I'm going to rewrite the original problem. The original integral, that integral right there, now turns into this integral. All right, first, it's the A over X. What was A? A half. Watch the way I write this. 1/2 over X. I like to put my constants up there, even if they're fractions, because I'm going to push them out to the side anyway. All right? And then I have plus, what's B? 1/5. So I'm going to put 1/5 over 2x minus 1. And then finally, plus C, and C was negative 1/10. Negative 1/10 over x plus 2. All of that dx. Who has a question?
Just gotta continue. So you get A, B, and C. You put A on top, B on top, C on top.
Yep, just using that decomposition.
How many pages does this normally take?
It depends on how big you write and stuff, but it's going to take up quite a bit of space, right?
We're allowed to bring work paper with us to the test, right?
I'll try and provide you enough space, but you can always take out paper if you need it. All I did here was just peel these constants out front, right? Just peeled that out, peeled that off, peeled that off. And now looking at each of these individually, we should be really comfortable taking the antiderivative of those. So here I go, antiderivative time. 1/2 comes for the ride. The antiderivative of 1 over x is natural log of the absolute value of x. Plus 1/5 times, careful, 1/2. Because there's a 2 here, you have to scale. 1/2 first, then your natural log absolute value of 2x minus 1. Right? That 1/2 is to compensate for that number in front of that x. And then minus 1/10 natural log of x plus 2. Here we don't have to scale because there's a 1 in front of that x, and then plus c. We're done. There you go. It's a bit of work, huh? How are we doing on time? I see that quiz. This is why I hate having quizzes in here. It just eats up too much time that we don't have.
We had a quiz today?
Yes. All right, so I want to go back, and I want to go back to where I said short method, and I need to show you the long method, which won't necessarily be good for this problem, but it'll show you for the next problem what we're going to do, and it'll give you something to compare it to. So back when I was at this point where we had, it was x squared plus 2x minus 1 equals a over x. No, we had already cleared the fractions. A, and then it was 2x minus 1, x plus 2, and then plus b, and then it was x, and then x plus 2, and then it was c, and then it was x, and then 2x minus 1. Right? Go back and look at that line right there. Right? This is where we were, and I said, let's do the short way. The long way, let me first tell you, what would tell you to do the long way? Well, if you can't do what we just did with the short way. If you can't kill off, like to get A, we could kill these off, right? We could kill those both off. There are some problems where you will not be able to kill these off. Like you can't plug in a number that makes them go away. And so you have no choice but to do the long method. You would, if these were quadratics that were irreducible or something, like let's say one of these factors was x squared plus 4. You could never kill that off. So you'll see, we're going to do an example. Okay, so the long way, here's what you do in the long way. You have to take the right-hand side, you have to multiply everything out. So you have to actually, like I'm going to FOIL this first. So I put A here, let's FOIL that. So I'm going to go here to here, 2x squared. Here to here, 4x. Here to here, minus x, minus 2, right? I FOIL that out. Then I pass an A through everything. I'll also collect those together. That's 3x right there. So this would become, watch how I write this, 2ax squared plus 4ax. No, 4. I changed that to a 3, didn't I? Yeah, 3ax. And then minus 2a. Okay, so I've FOILed this out, collected like terms, and then passed an a through all three terms. I've only done that. I still need to do these, right? So on these, I can just take the entire bx and just pass it through. So get bx squared. And then here to here, I get plus b times x times 2. I'm going to write as 2bx. And then the last one will be, I'll put it under here so it's on camera. It's cx squared. Oh, no, 2cx squared. 2cx squared, that's here to here, and minus cx. Y'all understand what I'm doing? Just multiplying it all out? So now I've got this. X plus 2x minus 1 equals, all right, on the left-hand side, or I'm sorry, on the right-hand side, I'm going to collect like terms together. So I have, this has x squared, that has x squared, that has x squared, right? Those three are all x squared terms. What I'm going to do is I'm going to write down those terms next to each other. So rearrange. 3ax squared plus bx squared plus 2cx squared. Those are the first three terms. And now let me look at my x terms here, here, and I also have that one, right? Those three red ones are all x terms. So I'm going to put those next to one another. So plus 3ax plus 2bx minus cx. And then I still have one more thing that I haven't accounted for. What's that? Minus 2a. Okay, so that's just reordering things, right? You'll see where I'm going with this. Just let me continue. This is actually a pretty cool thing that we're about to do. Equals. Okay, the first three all had x squareds, right? So I'm going to pull an x squared out of those three terms. Normally when we factor an x squared out, we pull the x squared out to the front, wouldn't we? There's nothing wrong with me pulling it out to the back. Let me write it down. You just tell me if you agree. 2a plus b plus 2c, and I factored the x squared out the back side instead of the front side. If you multiply that through, you get back those three terms, right? No? I'm going to do the same thing on the next three terms, these. I'm going to pull an x out, but I'm pulling out the back. So I'm going to write plus 3a plus 2b minus c, and then there's my x. And then finally, I have a minus 2a in the back. There's nothing to factor out there. Right. All of that was just to be able to do the next step. This is an equation, right? We must maintain balance on both sides of this equation, right, for it to be true. That means whatever number is in front of x squared on this side should be equal to the number I see in front of x squared on this side. And this is the number I see in front of x squared on this side, right? Those two must be the same, which means I can write this equation down. 2a plus b plus 2c must equal 1. Do y'all agree that that has to be true? That that number, whatever this turns out to be, must match up with the number in front over here. So I have right now one equation, right, with 3 unknown variables. Well, not yet. We need more equations to be able to solve. Well, where am I going to get my next one from? Well, whatever's in front of x has to match with whatever's in front of x over here. So my next equation is that 3a plus 2b minus c must equal what? 2, the number in front, right? The number in front. 2 equations, 3 unknowns. I need one more equation and I can solve this. But I have it, right? What is it? Yeah, this right here is a number, right? This does not have an x in it. That's just a number. Whatever a is, negative 2 times a is a number. That must match that number, right? So that's my third equation. That negative 2a, it doesn't matter. I'll write it like this. Negative 2a must equal what? Negative 1. And back in college algebra, this would be considered a system of equations, system of linear equations. I'd have to go back and look. You mean for partial fractions? Oh, system of equations, I don't know. Yeah.
Was this also called a matrix?
So when you get to systems of equations in college algebra, sometimes, depending on your teacher, sometimes you would talk about matrices, and then how do you solve? Well, but matrices are just an easy way to look at systems of equations where you don't get, the variables go away, and it's just easier to work with numbers. So, yes, you can. All right. Here for this problem, though, look, we don't actually need to work that hard for it because we can actually look at this right now and say what A is. Right? So, yeah, right. If we just take that first equation, you just go solve it, you get A is a half, right? So just by looking at this, I know A is a half. Does that match with what we got earlier with the short way? Yes? Yeah. It does. Yes. Yeah.
Most things have most things.
So the question is, how do we go through the rest of this, right? How do, you know, plug in, right? Okay. So we need an efficient way to solve this system of equations that doesn't take us 20 minutes, right? So what I'd like for you to do is next class, make sure if you have a graphing calculator that you bring it. Does anyone not have a graphing calculator? Do not? Do not? Do not? Okay, then I recommend that you go across the hall after class and you go check one out for the rest of the semester. Because I'm going to teach you all how to use your calculator to solve a system of equations. And that way on the test, when you get to a problem like this, because right now we have 3 equations, 3 unknowns, right? Your test might